All right, so here, let's talk about this program.
Yeah, it's on, I think. There's a timer going with the red dot.
Then let's go with that.
It's alright. Clayton's smart enough, and so is Vaughn.
Skippy?
Who?
Skippy.
I don't know him.
Yeah. All right,
I do not
so
recognize him.
as you go through this, you have to keep track of what you can control. So the photons coming in, and the short version of that photon energy is E equals hc over lambda, okay? And you're controlling the wavelength. So this part controls the energy. Your intensity does not alter the energy, okay? Your intensity is solely the number of photons that are striking the cathode, okay? That's it. All you're doing. So, and that was kind of counterintuitive. They thought, hey, even if we don't have the photoelectric effect, initially they thought, well, maybe if we increase the intensity of the light, we could still get the photoelectric effect. But then that didn't happen. Then they had to conclude that, wow, the only thing that determines this is the energy of the photons coming in. So you can calculate that energy of the photons coming in. Then if, when it strikes that electron, if it overcomes the work function, then that electron is going to get kicked out. So then once the electrons are kicked out, and what you'll see is this program actually does a fairly decent job. You'll see that the electrons are leaving with various amounts of energy. And the reason being is that because if you consider like almost like a gravitational well, so if the electrons are closer to the edge of that electron cloud, then when that photon strikes them, it gives them energy, and they're going to leave with a lot of energy because they're not so tightly bound to that nucleus. The electrons that are closer to the nucleus, they're further down like that well, because they're going to lose more energy to get out. They're not going to have as much energy when they leave. So that's going to be one of the questions when you get to the bottom of page 2, where you're going to return the metal back to sodium, and you're going to set that voltage to negative 0.64. And so what you should see on that one is that some of those electrons are going to go ahead and make it all the way across, and some of them are going to stop and they're going to get repulsed. So those ones that are stopping and being repulsed are the ones that were deeper into that gravitational well. So it costs them more energy to get out, so therefore they don't have as much energy when they go across, therefore it's easier to stop them. The ones that were on the edge of that electron cloud, which don't lose as much energy in escaping, those are the ones that go ahead and make that across. So when you get to question number 23, if you haven't done question number 23 yet, here's what I'm looking for. You want to put enough energy in it from the photons that you get a current, okay? I don't care what it is, but you want to make sure that you get a current. Then use your battery to stop it, okay? So your battery is going to give you that stopping potential. So that stopping potential, you're going to know that value. So if you look at the end of the day, you're going to look at that K max equals hc over lambda minus your work function psi. So you're going to figure out how much energy it takes to stop that voltage. You're going to calculate how much energy the photons had, and then you're going to work backwards and you're going to find the value of the work function. Once you find the value of the work function, then you're going to go to that table, and then you're going to figure out what that metal is. So that's kind of the process. What you should see on that work function, it should make a fairly decent GPA. Okay, not great, but not bad. okay,
On 22?
on 21.
21, yeah.
Yeah. So on 21, that work function should make it not horrible, but not bad GPA. But what I'm going to grade mostly on that is your procedure. I should be able to take Cassidy's procedure, give it to Isaac. Isaac should be able to take that program, plug in whatever she does for wavelength, stopping potential, whatever, and get the exact same results. So don't write that procedure for you. Write that procedure with the mindset that, hey, I'm going to give this to someone else, and they've got to replicate my results. That's the mindset that you want to have. Now, when you get to 23, kind of through 27, okay? So let me explain this mindset on how I wrote these particular questions. So on 23, you've returned this to sodium. You're going to set the wavelength to exactly 300 nanometers, okay? And you've got a voltage of negative 0.64. So you can keep that voltage, and what we're going to assume is that the distance across the plates is 1 meter. So this is this distance across here, okay? You're going to set that as 1 meter. Okay, we're going to change that later on, but for the sake of this argument, that's going to be 1 meter. And you've got a negative voltage, so what you want to figure out is what's the force acting on that electron, and then you want to calculate the acceleration of that electron, okay? Now, that acceleration on number 23, if you do it right, is 10 to the 11th. Okay, it's a really, 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 really big acceleration. Okay? Now, when you get to 24, I'm going to give you the work function, 2.304. You're going to calculate basically the energy of that, of 2.304. You're going to know the energy of the photon, and on this one, I'm going to say, hey, don't worry about the negative voltage. I just want you to figure out basically how much energy that thing's going to leave with, and then that's your kinetic energy, and then what's the velocity going to be. So if all goes well on number 24, you should get a velocity of 10 to the 5th. Okay? Then I'm going to ask you some questions about the de Broglie function, the de Broglie equation. Okay? Now, on 26, listen to me on 26, okay? On 26, I want you to have this visual, that you're shooting this electron out with the velocity that you found up on 24. So in other words, I'm going to shoot this electron out at 10 to the 5th. You're going to know your acceleration that you found up on 23. So you're going to know the initial velocity is your answer to 24. Your acceleration is the one on 23. You want to figure out if you could let this electron go all the way across. So your answer to 26 is going to be bigger than 1 meter. So in other words, I'm going to separate these plates out so that that electron, when it shoots out, is just going to go over and then stop. Okay? So don't use, on 26, do not use a distance of 1 meter. You're trying to find the distance, okay? It's like me throwing this ball up in the air with a certain velocity, okay? How high is that ball going to go before it reaches its maximum height? Okay, so you're going to use that equation on 26, and then you're going to use that equation again on 27. Now, when you get to question number 29, okay, you've got to follow the sequence on when that voltage is set back to 0. Up there in the top right-hand corner, you can set different graphs. So you're going to graph electron energy versus light frequency. And you're going to slide the scale to adjust the wavelength to generate a graph, da-da-da-da. So you're going to do this for sodium and calcium, okay? So when you draw this graph on 29, when you get done, it's gonna look something like this, okay? When you get done, that's what it's gonna look like. Label them so I know which one is the sodium line and which one is the calcium line, okay? Make sure that you label both of those lines, okay? Now, then you got some questions to answer about that. Then you're going to, on you get to 33, you're going to draw a current versus voltage graph. And you're going to predict, now stay with me how, again, through the spirit of how I wrote this question. You're going to predict what that's going to look like, okay? Then you're going to explain the basis of it. Then you're going to bring it up, and I'm going to sign off on it, on 35, where it says the viceroy of voltage, that's me, okay? Then you're actually going to generate it, and then you're going to see what it looks like, okay? So there isn't necessarily the right or wrong. You're going to say, hey, this is what I think is going to happen. When you get to 37, again, you're going to draw two graphs, one for sodium, one for calcium. And then you've got to do some explaining. So I'm done. You were on your own. This is going to be due on Monday. So there we go.